Hey everyone. So today we are talking about isotopes and atomic mass. Okay, basically, how are these two things related to each other? So, our learning intentions and success criteria for today are to understand how the atomic mass of an element is determined. That's our learning intention. And our success criteria is I can explain how the atomic mass listed on the periodic table is related to how common each of an element's isotopes are. So, today we're going to talk about three different topics. We're going to talk about isotope abundance. We're going to talk about something that I'm referring to as the problem, meaning the problem with calculating the atomic mass, and then how we actually do calculate the average atomic mass. Okay, so first I want to talk about isotope abundance. So the question is, how common are isotopes? So while each naturally occurring element has isotopes, these individual isotopes of an element aren't found in the same amounts in nature. Some isotopes are more stable than other isotopes of the same element. So this means that the majority of an element's atoms could have one mass number, while very few atoms have another mass number. Sometimes they're more balanced, but sometimes it's really not very balanced at all. Okay, so we need a way to calculate how commonly each individual isotope is found. So, what we have is a calculation called relative abundance. Now, this is sometimes called natural abundance, and it's a measurement of how commonly a given isotope is found in a naturally occurring sample. Basically, how common would a particular isotope be if you had like a container of that element? Okay. So here's an example of what I'm talking about. So here we have the three isotopes of hydrogen. So we have hydrogen 1, hydrogen 2, and hydrogen 3. Now, hydrogen 1 is commonly called protium. And we can see if we look at the natural abundance right here, that protium makes up 99.98% of all hydrogen. Most of it is protium. And protium is this one right here. It's one proton with an electron around it. Okay. Now, remember, it's called hydrogen 1 because its mass number is going to be 1. It's got one proton and no neutrons. Hydrogen 2 is commonly known as deuterium, and deuterium makes up just a very small fraction of a percent. It makes up 0.0115%. Okay. This means that if you had a container with 10,000 atoms of hydrogen, only one of those would be deuterium, most likely. Okay. So it's not very common. And then lastly, we have tritium. Tritium is hydrogen 3. You can see it right here. It's got one proton and two neutrons. Okay, so it's still hydrogen because it's only got one proton, but it's got a mass number of 3. Tritium is very, very rare. Tritium is so rare that it doesn't actually even have a calculated natural abundance. That means that in like 1 in a million um, atoms may be a tritium. All the rest are going to be protium and deuterium. Okay, so as we can see right here, it's not exactly balanced between the three isotopes. Okay, so this leads to the problem. Okay, so what do we do when an average is not enough? So when it comes to isotopes, there are some problems with calculating the average mass for an element as a whole. Okay, let me show you a little bit of what I mean. Okay, let's switch to my spreadsheet right here. So on this spreadsheet, I've got the three isotopes of hydrogen. Okay, I've got hydrogen 1, hydrogen 2, hydrogen 3. Now, if I just take the average of this, I'm going to do it the same way I showed all of you. Hit the equals sign, start typing the word average. See it right there. And then I'm going to highlight those three and hit enter. And look, if I take the average of the three isotopes, I get an average atomic mass of 2. And that kind of makes sense, right? Because 2 is in the middle but of 1, 2, and 3, right? So that does make sense. But there's the problem, right? Because we know from that previous slide over here that most hydrogen, 99.98% of it, is protium. It has a mass of 1. So if you were to take just an average hydrogen atom, it's probably going to have a mass of 1. So why is it that it can have a mass of 2 like that? Why is the average mass allowed to be 2? And the reality is it's not. It can't be. That doesn't make sense, right? So we can't just take an average. We have to do something different. Okay. So in comes average atomic mass. Okay. So because atoms are so small, there's simply too many to count individually. You can't just sit there and count them individually. And this makes achieving an average really difficult to do. Because remember, to calculate an average, you have to get all of the values together, right? So like you'd have to get all your atoms and you'd have to line them all out and go, okay, 1, 1, 1, 1, 2, 3, 1, 3, 1, 1, 1, whatever, right? But the problem is there's trillions and trillions and trillions and trillions and trillions and trillions and trillions of atoms. So we can't just sit there and count them all, okay? And we already talked about this before. To get even one deuterium, you'd have to look at 10,000 atoms at least. That's a lot of work, right? So we need a more efficient way of doing this. So as a result of these issues, the mass listed on the periodic table needed to account for not only the individual masses of the isotopes, but also how common those isotopes are. So the average atomic mass listed on the periodic table is determined by multiplying each of an element's isotopes by its individual relative abundance and then adding the values together. So it basically takes the mass numbers, multiplies it by the natural abundances, and then adds them together. Let's try this out. So I'm going to move that over there. I'm going to put this over here. Okay. Let's move to my next spreadsheet. Okay. So here I've got my isotopes. Oh, right here. Okay. Here I've got my individual isotopes of hydrogen. Okay. I've got mass number 1, mass number 2, and mass number 3. Now they're slightly different than exactly 1, 2, and 3, and that's because of the slight variances with the individual subatomic particles. And here I've got the natural abundances written as decimals. Now remember, if you're going to write a percentage as a decimal, you have to divide it by 100. So instead of 99.98%, I have 0.9998. Okay. Now what I'm going to do is I'm going to multiply equals, I'm going to multiply the mass number and its natural abundance. Okay. And luckily, the calculation's smart enough to figure this out. Okay. Now what I'm going to do is I'm going to take the three of these and I'm going to add them together. Equals sum. Sum is just adding it together. And I'm going to highlight all three of those, hit enter. And I get an average atomic mass of 1.0079. Okay. Let's check that against the periodic table. If I find hydrogen right here, I can see that the atomic mass listed is 1.008. That's the same as I got. If I just rounded this to the third decimal point, it would be 1.008. So my data is in agreement with the data that's listed on the periodic table. Okay. So what's important for you to understand is that the average atomic mass listed on the periodic table is determined by multiplying each of an element's isotopes by its relative abundance and then adding each of these values together. So it's not just how much mass does each isotope have, it's also how commonly are we finding this in nature. Okay, it takes both of those being factored together to determine the atomic mass. So, with that being said, we're going to end it here. If you have any further questions about this, come see me anytime.